Right, thank you for having me here. So I will continue the series of talks on shared prismatization. So last time I defined this notion. And just as a quick reminder, so I recall that the key input was a certain ring space, double check. Well, it's not quite a ring scheme, but it's we think of this as a functor from idempotent rings to actually not only rings to delta rings. And so the definition of W check was the following, it's just a biology. So we take the ring of bit vectors, and we take the fiber product over Q with Q curve. So here Q is defined to be the quotient stack. It's actually it's a functor from idempotent rings to rings. So it's not quite a stack, but it's not representable by natural scheme. So here W is the ring of bit vectors, and W hat is the ideal inside W that consists of all bit vectors whose coordinates are nilpotent at almost all but finitely many articles. So and Q curve. So there is this ideal is stable under Frobenius, and Q curve is linear function. Okay, so this W check has a little bit more structure. It has a kind of analog of Verschiebung. So W, there is an action of V here, and there is an action of V here. But in general, Verschiebung on Q does not commute with F. So there is no way to leave the nature of Verschiebung on Q to Q perf. But it turns out that you can, well, first of all, you can do it literally when P is greater than 2, because when P is greater than 2, Verschiebung on P commutes with Frobenius. But when P is greater with equal to, you have to modify definition of Verschiebung a little bit. Namely, we introduced P hat, that's a map from W to itself, by the following formula. So that's pseudo Verschiebung when P is greater than 2, and P hat of X is equal to V of Müller of -1 times X when P is 2. And so then the key observation is that we have this commutes with F. It's actually equal to force reduction. That's multiplication by P in Q. And in particular, so this gives Verschiebung on all objects appearing in this definition. So in particular, it gives we have on W. All right. So just to remind you how this we had the check and Q, how did it look like? So I want to prove a lemma that was a generalization of a lemma that Hugh stated last time, but didn't prove. So the lemma is the following. So let's consider W hat of R. So W hat of R definitely maps to W of mean radical of R, right? I can apply the well, for any functor from rings to rings, or even more generally to pointed sets. I can evaluate this functor on non-unitary ring, right? You just formally add a unit, and then you take the kernel of the projection from mu R plus C to W of C. So this is a well-defined object, and this sits inside W. So on this, this defines a map from Q to W of GA bar. So I recall that GA bar of that's notation that was introduced last time for any ring R. This is co-limit perfection of R. So this is a functor. So this receives a map from R reduced. But a functor from rings to rings that takes ring R to R reduced is not a sheaf. And this is the sheafification of them. So, right, so the main property for me here is that this is a sheaf. So if I take the quotient of W of R by W hat of R, well, this maps to W of R reduced definitely, and that means that the sheafification of this quotient, which is Q, maps here. So so let's define Q infinity to be the kernel of this. Okay. So lemma so Q infinity is so it sits inside Q, and it contains another subgroup here, namely power p torsion, which is also the same as Frobenius. Right? So why is that? That is because multiplication by p here, as well as Frobenius, is injective. This is a W of a perfect ring. So that means that if I have any element which is killed by F in Q, it definitely dies here. So claim is that if I consider product of two elements, say Q infinity, Q infinity, the product is 0. So let's prove this. So, well, yeah, and maybe this equality follows from the fact that V check is injective. So, and that form. So suppose I have an element X in Q such that Fn of x is 0. And suppose I have y in Q infinity.
Right, x belongs to Q. This means Q of R.
Yes, for some income. So, right. So then, so what does it mean that that my argument is in Q infinity? Well, in particular, it means that well, I can this locally. I can write it as a Vit vector whose all coordinates are nilpotent. So then I can write y as w, sorry, Verschiebung of some y prime. So, well, equivalent definition of Q infinity is the following. It consists of all vectors of Q which are infinitely divisible by V check. It consists of all vectors that can be written in this form for every m. Right? Because if I have a Vit vector whose all coordinates are nilpotent, then in the quotient of W of R modulo W of W hat of R, I can write it as a Verschiebung of something. Okay. So now let's compute the product. So let's take x and so this is equal to x times Verschiebung of y prime. And now let's use projection. So the projection formula tells me that, sorry, that's, or maybe I'm not sure that this is the standard name for this, but so it says that it's equal to y prime multiplied by Frobenius of x. Huh? But this is different. This completes it. So corollary of this, so we have introduced this recheck, and that is a map from W check to W. It's just projection to the first factor. So I have a map from W check to W, and the kernel. Well, what is the kernel? Okay. Sorry, maybe I need more room. Where is it? Oh, right. Sorry. It's not here. So corollary is that if I consider the projection, so what is its kernel? So first of all, it's this map is surjective. This follows from the surjectivity of the Vit vector Frobenius and the Frobenius on W hat. And the kernel, well, I want to call it the state module of Q. And by definition, this is the kernel, the map from Q perf Q. We have this sequence, exact sequence, and the claim is that W check is a square zero extension. Check is this square zero extension.
So I think, could you repeat again, like why things in Q infinity are infinitely many divisible by this Verschiebung?
Well, so first of all, Verschiebung is injective. Therefore, when proving that something is divisible by V check, well, if it's divisible, it's uniquely divisible, and therefore my statement is law. And then I can write, assume that my x is actually my y is actually in the quotient of w of r by w atom. In general, it's a Schiffification, but it suffices to, after replacing maybe r by some faithful cover, I may assume that my y is here. I can lift it. So so what this condition means? So it means that y. What does it mean that y is in Q infinity? It means that if I write it as sum of AI, then AI I muted. So I claim that after replacing R by faithful cover, I can assume that my Y is represented by an element of this. But now but then Y is equal to so this is R equals 0, infinity. But then I can write it as V of R equals 0, infinity the I of AI plus 1 in Q, right? Because the difference is just the Techmüller of nilpotent element, which is in the. All right. So okay. So so then so we introduced last time shear prismatization. So for instance, CP shear prismatized is the quotient of W check team modular W check. So and so what is this? This consists of all so W it consists of all X in W check is such that image of X in Q curve is P times C. So I think maybe Achille gave another definition. So this is equivalent to saying that for any okay, so strictly speaking, it's R here. Submit. So equivalently, it's equivalent to saying that for any homomorphism from R to an algebraically closed field, the image of X in W check of this algebraically closed field, which is the same as W of that field, is P times C. That's it. So right, so that's the prismatization of ZP sheared prismatization, and it has slightly more concrete description. So okay, so let's see. So we have so first of all we have map from W hat to W check, right? So if you have an element of W hat, it projects to 0 in Q. So in particular, it has a preimage, canonical preimage, namely 0 in Q. Now, so let's consider this set. That's a subset of W, and I claim that there is a map here. So I explained that there is a homomorphism from W hat to W check, and P also lives here, namely, P in Q, of course, is not 0, but it's stable under the Frobenius, so it lifts to Q-perf. So there is this map, and now I can mod it out by W cross, W hat cross. Again, this is a non-unitary ring, but I already seen that if you you can take units of a non-unitary ring. You just formally, explicitly here you just take 1 plus W hat. But that makes sense for any non-unitary ring. So this is dimension. And so the claim, I think Achille proved it, that this map is isolated.
Do you is W check?
Oh yeah, sorry. Yeah, I also need to. Okay. So and then we have shear prismatization of a fine line, which gives over prismatized, and so I will just tell you what the fibers are. So if I have some C, which is a primitive, which is bit vector in W check. Then what you do, you look at R, you define fiber of this ring stack, living over C Sheared prismatized at point C is horn of the map from W check itself. So I have here ring R, so that's going to be a ring stack over a specker. Like W check, you pull it back to R, and then you consider multiplication by C. Okay, so and just notation that I'm going to use for W check, and I will put L here to emphasize that I take the derived portion because the step of anime. Okay, so that gives me a ring stack living over ZP Sheared prismatized, and having this ring stack, and we can define prismatization, Sheared prismatization of NX. By star wave points, just X of prismatized. See. this is a magical form. Okay, so now, so this definition here is parallel to the classical, well, to a more perhaps familiar notion of usual prismatization. So I recall that the usual prismatization of ZP is defined as a quotient of W, which is replaced everywhere, W checked by W. So, so what is W prime? Well, one of this definition. So you can consider all bit vectors in W of R, such that for any homomorphism from R to algebraically closed field, the image of X in W of A is P times. So this is equivalent to saying that the zeroth coordinate of the zeroth width coordinate of X is important, and the second width coordinate of X is. And then you have this this quotient presentation. So I want to compare this with the Sheared prismatization above. So I claim that if I have an element here, so maybe just notation. So let's call this W prime. And I'm going to refer to this as strongly primitive bit vectors. So, okay. So anyway, so there is a map. Any strongly primitive bit vector is in particular primitive. So there is a map to this quotient. Well, unfortunately, this group W cross does not act on the set of strongly primitive bit vectors. If you take this bit vector and multiply it by an arbitrary unit, it need not have this form. But let's see what acts here. So I claim that you can consider the group of all U in invertible bit vectors with the following property: F U minus 1 is in W hat. So it's not quite. So this group is slightly larger than the group that we considered over there. But if you apply Frobenius to this U, you get an element of W cross height. So, and an exercise is that this map, well, first of all, so I claim that this group acts really by multiplication. And the exercise is that this arrow is actually an isomorphism. Okay. So what does it buy me? So we have a canonical map from ZP. So first of all, observe the canonical map from ZP Sheared prismatized to ZP prismatized. Well, I'm going to use this concrete presentation. So you see that the spaces we take quotient of, they're just the same, but this group is slightly larger than that. So the map is just takes C2. And the claim is that so the map is the torsor. Torsor for the following group. You take the multiplicative group and you take the quotient. So you take the multiplicative group and you take the divided power whole of the multiplicative group at 1. And you quotient this group by its PD completion. So this is the PD completion of the divided power. So as a just as a functor from rings to sets, it assigns to ring R. This guy assigns to ring R set of all elements of R together with a compatible system of all divided powers. And here you require that those divided powers eventually. So these are groups. You can take the quotient, and this so what you I guess so this claim becomes complete tautology if you observe that this gem sharp is the Frobenius kernel on W cross, so F equal 1, and this is Frobenius kernel on W. Okay. Are there any questions? So then you play this definition. Okay. So let's if I give you a point here, a name for points here are Cartier with divisors. It's named used by Markov and Jacob. So in order to to define X sheared prismatized C, I need to leave this point to a point here. And the claim says that this lifting, well, first of all, it did not exist, even if this map is subjective as a map of sheaves. It need not be subjective on points with values in some fixed ring R. But also this lifting is not unique. So if I have a Cartier-Witt divisor, so a point here, I will refer to its lift here as a shearing of Cartier-Witt. So we learned that the space of shearings is either empty or it's a torsor under this guy. Well, let's try to compute this quotient here. So it's not that easy because so what is by definition an R-valued point of this quotient? It's a torsor over spec R for this group, together with a trivialization of its push out here, right? So in order to, I'm saying that the map from R points of GM sharp to the R points of this quotient is not surjective. So that's makes the computation a bit trickier.
So in other words, the difficulty is that this is a quotient in the sense
Right.
of flat sheets for the flat topology.
Yes.
So this requires some thinking
So-
and
Nevertheless, here is a concrete example of computation. So I don't know how to. So maybe before I explain this, so let's observe that this group is a map from mu p. So mu p has divided power structure. So there is a map from mu p to gm, and it extends, to do it uniquely over integers, to a map from mu p to gm sharp.
Maybe not extends, but how to say it?
No, over ZP. Over ZP, over ZP, it's unique. Just a question because
well, just are you thinking in terms of rings? Or
no, in terms of coordinate rings. Coordinate rings are Peterson.
So mu p, we have an obvious mu p is contained in GM.
Yeah.
In GM.
Yeah, I'm saying.
You have a map from GM sharp, and then the claim is that cysts are linked in this sense.
So on points, this map is very far from being injective, but well, coordinate rings are Peterson free, so therefore it's essentially it exists here. Okay, so so that's there is no map from mu p here. So this is a candidate for some non-trivial elements in this. And so here is an example. Suppose that so let's conclude this quotient for the following. I take ZP and I add p theta 1, cycloatomic extension of degree p minus 1. Then I claim that this map that I explained, so mu p of ZP is actually nice. And this is sigma pz, and well, the Sheareds are in this case, well, this are p. Oh, sorry. Maybe. Yeah. So to a concrete example. So let's take a point P here. Well, P is a p point, but I can consider it as a point with values in this larger ring. And then the claim is it has one shearing, right? I can just take P here. And but the claim is that there are many shearings, namely this point P here in ZP prism of this ring has precisely P shearings. Yeah. So you get P in U stacks, and so shearings of E in Z P this ring are well, you have one shearing and you can multiply it by Tech-Miller. Okay, so for instance, when P is 2, this is already ZP, so you get 2 shearings. Okay, so
X mean example or exercise? So what is?
Well, both. So I will give you a kind of, I explain an idea of the proof. So you have to analyze torsors over this ring for this group. That's complicated. I don't know how to analyze it. But be only interested in those torsors which are trivial when you take the push out to GM sharp. So the idea is to use 2 exact sequences. So for instance, the set of isomorphism classes, or even the group of isomorphism classes of torsors and under GM. By the way, there is crossed under GM sharp over any local ring, over spectrum of a local ring, is the co-kernel of this map. Why to respect related at that way. So because W cross, there are no torsors over spectrum of local ring for the group W cross. So here it's kind of more complicated. There are some non-trivial torsors perhaps even for even over spectrum of a local ring. But so Volodya proved a very useful result that if your ring is nilpotent and it's the reduced its quotient by nil radical is semi-normal, then there are no W headers. So that means that if you take any torsor here and you push it out, you make from this torsor and the W head cross, it's trivial. So and this applies to a ring like this. So we observe that the isomorphism classes of torsors are one-to-one correspondence with the co-kernel. So and then you have to check something like this. You have to check that if you have an element of W cross hat, which is Frobenius image of an element here, then it's in fact it's Frobenius image of an element. So this in general it's tricky, but for this particular ring, this can be.
So where does you so far in this cache of the proof you explained that some things are zero, some torsors are trivial, and so on. But eventually you will have
okay.
to get.
So here is a
where does it come from?
Okay, so here is a concrete statement which general statement which implies what's written here when p is greater than 2. So if so claim so suppose that R is R incomplete p plus complete and R mod P is semi-normal. Okay, and R reduced. R mod P reduced is semi-normal. Normal. And okay, so let's see. It's reduced and is similar. Then if x x Frobenius of x is in W hat, this element is in then x is W.
So do you require R mod P to be reduced?
Yes.
And to what R do we apply it?
Oh, just to
CP.
so sorry. So sorry, I don't require this. Sorry. What? Just this. All right. So I think this is in your notes.
One minus brackets minus 1.
P is greater than 2. Oh, I didn't say that. Yeah, so this lemma, this claim is sufficient to prove this assertion when P is 2. When P is 2, when P is greater than 2, it's slightly more involved.
I thought you would need that R mod P itself is reduced because because then you have the example of bracket zeta P minus 1. So bracket zeta P minus 1 is something such that F is.
Sorry, you are saying that. Yeah. So then X, I think X, then Frobenius X is in F. So I'm not saying that X then, yeah, I'm not saying that X is the here. Choose. Okay, does it make sense? All right. So so we have issues. Now so now let's look again at this, stare again at this. So so want to observe that. So we have this map. Let's call it canonical map. But now want to observe that we also have a map in the other direction. So the Frobenius. So the Frobenius map goes from CP prism to CP Sheared.
So the standard thing is the Frobenius from CP prism, and the Frobenius mapping from the CP sheared prism to CP sheared prism. But you are saying that there is something better.
Yes.
The Frobenius somehow does
right.
Yes.
So so how it works? So let's stare at these formulas. So and let's observe that. So I'm going to identify this with E plus W over W plus with the property that Fu or minus 1 is in W hat. So and let's observe that. So we have a map from here to E plus W hat over W hat plus that just takes C and send it to Frobenius. Right? So the idea is that under this map, this group maps to this one. So this gives me the Frobenius. And so if I compose it with the canonical map, then well we have F prime composed with canonical. So it's So it's a map. So I claim that this is just the usual Frobenius on Z shear prismatized, which comes from the Frobenius on W check. So Frobenius on W check preserve the subset of primitive vectors, and also position in the other direction. So that's a Frobenius map for the sheared prismatization of the point, and I claim that everything can be defined for any scheme. So in general, we have X prismatized, and it maps to X prismatized, and that's called map canonical, and that leaves over the map that I already defined. And that is Frobenius. So how it's defined? Well, I need to explain for you how to construct a map from GA shared prismatized at point C to the usual prismatization. And I didn't tell you what the usual prismatization is, but I will tell you now. So the usual prismatization of GA is by definition W mod C. You just replace the W check by the usual ring of it. And this is W check mod C. And the map, so this comes from the map from W check. Okay. So now let's define the Frobenius. So this gives me this. Let's define the Frobenius map. Okay. So Frobenius. So for this, it's convenient to use slightly different model presentation for GA shared prismatized C as a again as a quasi-ideal pair. Namely, he'll explain that alternatively GA shared prismatized C can be computed as a cone of the following map. You take W and you form the fiber product. That's a more economic construction. Instead of going all the way to perfection of Q, we just apply Frobenius once. So this is safe. And this is kind of this map is F, and this is the usual perfection. And this this DXC depends on well, it's given by the following formula. So if I have a bit vector, I will send it to C X, comma V hat. All right. So I claim that GA shear prismatization C can be alternatively described as cone of this map. And there is a map of quasi-ideal pairs, in fact, from the original presentation, from this presentation to this. So, which is a nice place. And that's what I want to use. So let's construct, construction of F time. So this construction of the canonical map, and this construction of F prime. So what does it mean? What do we have to do? We have to produce a map from GA usual prismatization to the shared prismatization, but computed at F. This will be the formulas. So I have to replace everywhere C by XC. And then, so my goal is to produce a map of, well, I will define this map. It will be actually given by a map of gain of quasi-ideal pairs. So, namely, so this is F, and the second coordinate is I believe that everything is. Okay, so this gives me this map, and so this is a map of fixed steps. So if this, it's enough with my general construction. It's Frobenius and canonical method.
So can you lift this?
Sure. Give just one example. So Frobenius and canonical maps still satisfy this, this refinement of the absolute Frobenius and the shared prismatization. So, so suppose I have some x over CP. Then we can consider the shared prismatization at point C equal P. Oh, sorry, this is the usual. That's
Is it also called the Durance?
It's also called the Durance. And so then we have the shared prismatization at point C equal P. And I think I will explain that if P is not 2, this is the shear Durance. Well, what you want to remember about this is the category of effects is smooth over ZP. Then the category of quasi-coherent shifts on this stack is just the category of OT. Whereas the category of quasi-coherent shifts here is the category of locally nilpotent modules. So then we have again this the RAM stack, and so having this map, we can look at the pullback functor on shifts, and so what we so I claim that so this map, a pullback along this map, is just an embedding of the category of locally nilpotent D modules into the category of all D modules. Whereas this second map, well, the pullback with respect to the second map is trickier. It's called the crystalline Frobenius. So if P is not equal to, then well, so the crystalline Frobenius gives you a functor from the category of all D modules to the category of D modules locally nilpotent.
So another, Thomas, I think you're just saying that if you, after Frobenius pullback, any D module becomes.
Yes, so there are two claims here. First of all, locally, this Frobenius pullback is constructed as follows. You take Frobenius mod P, you lift it to X. Locally, this is possible. For instance, if X is affine. And then I'm saying that if I have any D module, then its Frobenius pullback is locally nilpotent. Mod P has zero peak. But the second claim is that this construction, in fact, works globally. So you don't need a Frobenius lift on X to form the pull. But it doesn't work, however, when P is 2. There is no Frobenius pullback from all D modules on X to locally nilpotent D modules. It really depends on the choice of Frobenius. The functor depends on the choice. And this is consistent with the fact that when P is 2, this what you get here are not quite D modules, but something else.
Something what?
Something else. Yeah.
Did classical science consider this something else?
I'm not sure.
Not sure.
Okay, so I think maybe it's a natural would be natural time for a short break if we want to have a short break. Do we want?
Yes, we do the work.
Okay. All right. So so I want to say something non-trivial, and so I want to tell you about the theorem for sheared prismatization of delta. So yeah. So so suppose X is a delta scheme.
Just one preliminary question: is there a parallel theory for usual prismatization?
Yes, and I will start by that's a trivial observation, but I will start with this. So suppose X is a delta scheme. So for instance, you won't lose anything by assuming that X is just spectrum of P-complete so delta.
Delta scheme is a functor that a delta scheme is a functor that lands in delta rings, or
No. It's I mean
it's a defined scheme,
That's
and this A is a delta.
I mean, this is the example. Is this the whole always definition of a delta scheme?
no. It's I mean really a scheme. is a
Globalization.
okay. So represent. Well, so okay. So what is a so then for every R, we have a canonical map from R points of X to points of X with values in W. So so that's for instance, if X is a phi, then this comes from the map from A to W, which is given by the delta state. Okay. So, and this
just not so clear. So you are saying that, so what is X of R is...
just homomorphisms.
Can you write it a little bit more?
Yeah. Okay, so let me...
I understand that you thought about this for a while.
Okay,
so
okay, I will write it down.
Making...
So first of all, I want to give a name. I will, well, okay, maybe. Sorry, this name will be used for some other context. Oh, so so how it works? Suppose I give you a homomorphism from A to R. So that's a point here. Then, so what I can do, I can take the composition. Well, first I apply this map. And then, so if this is F, then I can take W of F. W is a function. So I get map to W. And so this is a point.
So your W delta comes from Joyal's junction. Yes. And in some sense, this W delta encodes delta. So my secret notation for W delta is capital delta. But anyway, of course, capital delta also means the diagonal. So, but anyway, so W delta is a way to encode delta. It's a unique homomorphism from A to W of A, such that if you compose it with a canonical homomorphism from W of A to A, you get the or in other words, W delta, to compute the W delta of A is the width vectors whose Joyal's components are A delta of A, delta square of A, and so on.
Okay, so in particular, I have C, which is a say W primitive bit vector. I can compose this map. I have a map from X to X W for and then I can take portion C. And this is, I recall that this is prismatization. So for any Xi, we get a map like this, and this assembles a map from X times ZP prismatized to the prismatization. So
Okay, so this takeaway is that for if X is a delta scheme, then you have such a conjunct.
Yeah. So this is a very important concept. And I can use Frobenius this F prime that we define to construct something similar for the Sheared prismatization. So I can map. First of all, I can map this to X prism, and then I can use F prime and to map it to X Sheared prism. So this leaves over CP prism, and this leaves over CP Sheared prismatized. This map is
just one. So the naive expectation based on ignorance would be that there is a map from X cross CP W sheared, the X cross CP prism sheared to X.
Yeah. Yes.
Is this?
Yes. So I will call this trivial observation.
Just one. So
let's give a name.
So this was my naive expectation that you can just put a hat over this.
Sure.
Find above.
Yeah.
And you're saying that this is indeed true.
Yes. So here is how I want to formulate it. So W this map. I'm sorry for using W too many times. Okay, maybe let's get it more careful. So I will call it. Factors is well, you have a map from X Z. Sheared prismatized X. Sorry. Prismatized, and this map is identity. Frobenius. And then we have something. So probably you refer to this expectation, which is indeed true. And this map is let's say. So concretely, it means that well, the map from so what it means is that the map that I defined here from X to X Sheared prismatized at C. Okay. So a priori
Yes. So you claim that there is a canonical map from X cross CP prism sheared, prism sheared. And is there a direct construction of this?
Yeah.
So far, you say that it exists. Maybe it is unique in some sense. I don't know, but
Yes.
anyway,
Yes. I mean, it's
construction.
yeah. I mean, it's just comes by unraveling. It comes from the map from W to W times Q over Q. So if you unravel the definition of Frobenius that I gave, so there is a map from W to this quasi-ideal pair. In fact, it's just a map from W to this object, which is given by Frobenius and identity. And so you have the sheared prismatization, the fiber of the sheared prismatization of A1 at point C is given by this quasi-ideal pair, and so the claim is that this quasi-ideal pair receives the map from W, and then applying transmutation, you get.
I want to write this down somewhere.
Yeah,
so
yeah.
So I was able to write down your definition of the map from X
to X of R, maps to X of W of R, maps to X of W on C. That's precisely X placed.
You were saying that in the non-shear story, the main point is that was that the ring stack, the prismatization of the fine line receives a map from W. And now you are saying that the shear prismatization of the fine line also receives a map from W. No, not.
Well, it's note this Frobenius here. So there is a map from here to W, one of multiplication by C. This is so this is the quasi-ideal module for the sheared prismatization of a fine line or point C, and this is the quasi-ideal module for G. So the composition is not the usual map. It's Frobenius recomposed with the usual map. So this composition is given by the Frobenius.
Is whether they should be C's or F of C. So it seems like on the top board there, it seems like the first map lands you into the fiber over C, and then you apply F dash to that, so you're over the fiber of F dash of C, right?
So sorry, what? I'm not sure that I understand the question.
Oh yes, okay, yeah. So there's an F dash here. Why isn't there an F dash later on?
So that's the claim. So the claim is that this map depends only on F prime of C prime.
Okay.
It doesn't depend on C prime itself. And well, I constructed it for you.
So does C mean F prime of C prime?
Yes. Yes.
I see.
Mhm.
Okay, so she got redefined between the top there and the bottom.
Okay, so this is a trivial observation. So we have this map.
Just so, but and uh, but this is your construction or alternative definition is given on that blackboard.
Yes.
So what is this? So you first use the map from R to W of R, which encodes the delta structure, and then you use the map from W to and then I think you use again the map from W to the prismatization of a fine line. And why? What is the role of this map from W? So you wrote the map from. Can you erase, in principle, the map which has over it F, comma, identity? What was the role of this?
No, I mean, I need to define a map from W to this fiber product.
I do have it.
Because the sheared prismatization of that fine line is the cone of this map. So this is
so you
this
use
is GA sheared prismatization.
Sorry. Yes, I was confused with up and down and left and right. So it's I thought that the description of the prismatization on the fine line as the code of the D immediately gives you the map from W to prismatization, but in fact it doesn't because you have this W. W is something. This realization gives not a map from W to the cone, but a map from the cone to W shifted by 1. You are saying that let's use something else to have a map from W to the fiber product, and then of course it gives you a map. Okay.
So
just a moment. Last time, Akil gave several realizations of the sheared prismatization of the fine line. And I think one of them was represented as a cone of something mapping to W. So if you use, I think, if so, then this means that everything is obvious, literally as the non-sheared case, if one uses not this realization of the sheared prismatization of the fine line, but another one, which is probably the realization from your October. Am I right?
Yeah, I can write it. It doesn't lead to a stronger result. So the other realization was the following: you take the same guy. This is Frobenius, and then you observe that there is a map from here to here. That's exactly the same map.
Yes.
That's exactly the same map. And then you observe that this map is surjective. Therefore, when you form the fiber product, the map between the cones is an isomorphism, and that was the other present. And then, of course, you can map identity. Well, W here.
Yes. So my point is that here, if we use the role of this map from from W to the fiber product W cos Q is some sense to switch from one realization of shear prismatization of the fine line to another one, to the one that you gave. At this moment, we don't care what IC is, but yes. But so the important thing is that the shear prismatization of the fine line receives a natural homomorphism from the epimorphism from W.
Right. So now I wanted to at least explain one kind of non-trivial result, and that this result, well, was suggested to us by Devon Menon.
By whom?
Devon Menon. I think he's a graduate student at Northwestern. Right, his name. So suggested by So the theorem is the following. So let's look at this picture here. So for any delta scheme, you have this map. So the claim is that there is a canonical, natural descent of first of all of X sheared prismatized and also of this map. To the usual prismatization. This means the following. It means the following. So we have first of all we have a we have some step which leaves over the usual prismatization of TP. And we also have a map from X to ZP. So this is this leaves over ZP. Okay, so there exists. Sure. So there exists.
So this is a theorem hyphen construction. Yes.
Yes.
So you are going to construct something.
Yes. Let's go back. Go back. To ZP. Is well is the map that I defined here. So X X X X so what happens here? So first of all, I introduced notation. So this is a new notation. So this is a step that leaves over the usual prismatization, right? There is no head here. It leaves, maybe since it's not visible, let me write it here. So it's CP. So this is it. It leaves over the usual prismatization, and it's pulled back to ZP sheared prismatized is this object that we defined. So I explained that in general, the prismatization depends on the shear. The shear prismatization depends on the shear. So we have a map from this stack to we have a map from CP shear prismatized to Z. And we observe that the fibers are, well, that this is a torsor for a certain group, G sharp modulo G, GM sharp. So, so in particular, if I reduced looking at particular point here, we produced its P shearings, and this gives to different ring stacks. But the claim is that when you apply the sheared prismatization construction to a delta scheme, the result does not depend on the shear. It depends only on the usual Cartier bit difference. Okay, is the statement clear?
It's in the process of becoming.
So, for instance, when the point P, ZP point, well, P, ZP, has two shearings when P is one is called corresponds to what we call sheared drum stack. The other one is sheared crystalline stack. So the two shearings are, well, there is a P in CP, and there is also phi, which is P times 91. That's another. These are two shearings of the same point when P is 2. And so for any X, you have two stacks. One quasi-coherent shifts on one stack is OD modulus. Quasi-coherent shifts on the other stack is something. But the claim is that if X has a delta structure obviously, then the two categories are the same.
And did Manan just guess that this should be true, or did he? So what was?
Okay, I will explain. I will explain it in a second. He gave a talk here. I think the title of his talk was the completion of Drifted's formal group.
I remember the talk.
And the statement is related to this decompletion, and I will explain how. Right? So he gave a talk. Well, his construction uses, I think, THH. So there is an alternative construction, which is a priori. Okay, so the proof. I wanted to give a proof. It's was explained to me by Hugh, and it's difficult, at least for me, in the sense that it uses some little bit of higher algebra, but very nice higher algebra. It seems very important. We arrived to this statement by looking at one example that I want to describe first, very concrete example, related to the completion of the Drifted formal group. Perhaps we arrived to the statement because they haven't told us that it should be true, but also we did one computation. So before I explain this kind of slightly abstract proof, I want to explain how it works in an important example. So example. So let's consider apply to X in GM. So GM is multiplicative group, and the delta structure. It's important that it's a delta group. So delta of C is 0. So Frobenius takes Z to 5th power. So there is a delta structure on the Afan line, but you can make GA the delta group. So that's GM is much better than GM. It has Frobenius leaf compatible with the GA. So in particular, what we are saying is that there is a map from GM. Well, we already have a map from GM that is C. Here prismatized to GM. And that's what we already defined. And the theorem says that this map descends canonically to ZP. So I want to do this.
So descends to a map from where to where?
So descends. The map descends to a map from GA. GM. So I don't know. I have to define this one. I'm just repeating this.
Maybe just so you have this before descending. You have a map from GM cross CP. Prism, sheared prism to the GM sheared prism. What kind of map?
So this is a group homomorphism.
The group homomorphism.
That's because the delta structure.
Is it an epimorphism?
Yes. So the claim is that okay, I'll erase this. That doesn't say anything. So we have this map we already constructed, and that is the claim is that it's surjective. Which is an easy.
Yes.
So let G be its term.
Yes. So it because it's surjective, it represents GM sheared prism. It's a quotient of GM of CP. So for each C, it represents GM sheared prism of XC, the fiber of XC. It's a quotient of GM by something.
So what I'm going to do, so I want to prove this theorem in this special case. So what I'm going to do, given a point C in CP sheared prism, we describe this G C GM explicitly. And we will see that the answer depends only on the image of this C in ZP. And this will prove the theorem. So I will write down the formula for it. So to write down the complete formula, I need to go. Well, we have to use some model for the sheared prismatization, and so the model that I'm going to use is the most economic model. It's not this one, but it's rather it's rather the pullback along the map for any state. So so whenever I have so I think of ZP as portions of W plus one of W course. And suppose I have
Just so we have two slightly different models for the prismatism. And which one else we are using?
I'm going to use this, and I will write down explicitly what the definition of the fiber product. So suppose I have point C, which lives here, and so what is IXC? So it's by definition of the fiber product, it consists of pairs X Y in X Y W such that Frobenius of X is equal to C Y and X minus V Y is in W. Okay. So I'm just unraveling definition of the fiber.
Yes.
Now let's describe H, this G C profile. So let's write down the functor of this. So the functor of this. Okay. Here. So what does it mean to give an element here? So what is G, right? So we are computing. We have GM made into GM C, and here I have everything. C is W R, summary R. Everything happens over summary R. So and I have a map from spec R given by 1. This is a group. So in particular, it has a natural. So and what I want to do, I want to describe the fiber. So this is GM. Oh, sorry, G. Okay. So that's my goal. So in particular, given an R point here is, well, first of all, I need to specify an R point of G. So okay, so I have to specify a vector here, an element here. Plus, so once I have an element here, it gives me an R point of this step. So how this R point is constructed? Well, it's constructed. So I have a map from coordinate ring of GM to W. So coordinate ring of GM, the coordinate is Z. This map takes Z to
a naive guess would be just that we have to replace W by its multiplicative group and XC by so to say, its multiplicative group. So we are. I think we're trying to. You are trying to explain the following. So how to compute the multiplicative group? So we have a ring stack, namely the cone of the map from IXC to W. Now a ring has a multiplicative group. The ring stack also has it. And what is probably it is a naive guess would be that you have to take the cone of the map from IXC to the multiplicative. Yes, just put cross.
Yes,
cross everything.
Yes. So what is the formula? So given a point of R cross, we have a point of this of GM of GMC, and I need to specify a homotopy between this point and point 1. And I claim that it's specifying this homotopy is equivalent to specifying an element here whose image in W is Pech-Muller of X. So okay, so this is Y W such that Pech-Muller of X, right from this is equal to 1 plus V check plus plot C. Okay, so again, so there are 2 points here, R-varied points here. One point is 1, and the other point is Pech-Muller of X. And what does it mean to specify homotopy? It means that I have to leave the difference between these 2 points to a point here.
So I think some brackets are missing. So you write GC of R is what? Is probably the set of pairs.
Right.
And so if you write a pair, you have to put.
Yeah, that's why I haven't finished. Okay, so
a set of pairs X, Y, where X is.
So this is one condition. I have a formula for.
And then also some other. There is the other.
The other condition. And the other condition is that that X minus yes, that X minus 1 minus V check of Y is in W. That's a fact. So I described the fiber, the kernel of the group. That's just a functor from rings to groups. It might be not representable by an actual algebraic group. It's representable by some group in the file. In the fine schemes, but that's at least this is a group. Now, so what do we want to check here? So we want to check that. So a priori, this group depends on the choice of the ship. It's easy to see that when you multiply this C by a unit, by an invertible element in W hat, the result that the dual group is canonically isomorphic. I will write down the form. But it's not that obvious that it does not depend on the shape. So what we want. So I recall that. So we had a have ZP. This is description of the shared prismatization of ZP, and we also have a description of similar description of the usual prismatization, and this is W hat plus P over some larger group. Namely, you look at all U in W cross, such that Frobenius of U minus 1 is in W. So what we want to construct a canonical isomorphism between G C and G U times C, where U lives here. Moreover, we want this canonical isomorphism to be compatible with the forgetful map. So I will write down the formula for you. So the formula is very simple. Suppose I have an element here. So here is an explicit description of the group. So I have X in R cross X and 1 in W R. So what can we do? We can send it to X and then U inverse times Y. Yeah, so if my U equation is the same equation except that C is replaced by C times U. So the only thing to check here is that this condition is still satisfied. That means that X minus 1 minus we check U, or we had U inverse 1 is still in W hat. So now this is something very concrete statement about width vectors. So we have X and Y that satisfy these two properties. Now the claim is that then this difference is in W. So if I prove this statement, then the theorem, the descent of G, even of this sequence to ZP prism, will be constrained. Mm-hmm. So let's prove this. It's yes or no question. We don't know. No, we don't have to. It's already not a question of construction. It's a question of verifying some this property. So what we need to check is that so we have this, and we want to prove this. That's equivalent to saying that U inverse Y minus Y is in W. So U inverse X1 times Y is in W. So it's 0 in. That's it. So, but now I want to recall the lemma that we proved at the very beginning. So Q P maybe F infinity. So if I have any element in Q which is power F torsion, and I multiply it with a vector whose all coordinates unimportant, then the result is 0. Let's use this one. So F U minus 1 is in W hat. Well, is 0. So that means that, well, U minus 1 is, that's good. So let's check that Y is here. But okay, so what is Y? Y is has satisfied this property. So we have that f of x. We have that x if power is equal to 1 plus well p y in q, right? Because c is equal to p, right? So but that's this in particular, it implies that, well, x is x minus 1 is
where do you get? How do you get that Müller effect?
Because C is in W hat plus.
And Frobenius
Müller is just
FX is just the.
So well, in particular, well, if you look at the if you look at the 0 Gauss coordinate of this, well, it's equal to 1 modulo p. So and R is p nilpotent. The ring R is p nilpotent. So that means that x minus 1 is nilpotent. Enough. Right? And it means that if I this implies that x p to the n is 1 enough. So that means that if I apply Frobenius, this is 1, and this is 1 plus b check fn y in. So, and this implies that fn of y is 0. So that means that y is in q f infinity, but we already we know that there is an inclusion. So q infinity contains this. So in fact we prove that that y is also. Therefore, the product is. So we can just apply the lemma and see that the product is. And this implies that this map is well defined. It's clearly isomorphism. So I want to summarize the claim. So first we looked at this this group, this sequence over living over double U hat plus. And then we showed that it's invariant under the action of this group on a set of strongly primitive vectors. The fibers, everything descends. So this gives me the descent of the sequence to ZP prismatized.
Is there, in principle, if you your argument is the idea of your argument is that it's multiplying C by something into priori out still doesn't change Hx. But another approach would be to somehow define Hc immediately for C being multiplicative of the any primitive element. That would be not necessarily strongly primitive.
Yeah. So maybe I will finish. I think it's kind of it's already.
I'm not asking how to
very
write
late,
it.
but I want to give a definition along the line that you suggested.
You are what?
I want to give a definition along the line that you suggested. It will be one line definition. It's kind of takes time to digest it. So I will give you a one line definition of so definition of X sheared prismatized machine. So again, the setting here is the following that we
Just is maybe is there a comma between before the question mark, because if you put a comma, otherwise we can think that you are asking it.
So this object leaves over CP prism, and it's pulled back along this map, canonical map. Just to call that what we want to do is X something that we already. That's what I want to construct. I want to construct this. So definition. So let's take some C in primitive. So it's usually it's not strongly primitive, just any primitive vector. So and I will tell you what are coincidences. So what you do, you look at X W mod C of R. It's one. The other object that you want to consider is X of Q mod C of now what you put here. So that will be the fiber. So you take X perf of Q mod C. So first of all, what is X-perf? X-perf is limit perfection of X along the forbiddance. So it's inverse. So this is delta scheme. So it has forbiddance. So I can define X-perf. And definitely there is a map from X-perf to X. So this gives me this map. And well, the fiber product is what gives.
The left-hand side is X prism shared question mark at Xi.
That's something. Yeah. So that's the answer.
And so it answers much more than I asked. I asked about this particular example, but this is an answer in general. And here, so the rule is that if perf is a superscript, then it's a projective perfection. It's a subscript, then it's now you are saying that it's very derived, and
no, I'm not saying that this is derived.
Already the original definition. Why is it more derived than?
No. I mean, no, this definition is I think it's understandable.
Yes.
I think since it's already very late, I don't want to. So the first claim is that if you take this object and you pull it back along this map, so namely, if you assume that C is strongly and that C is equal to P in Q, then you recover the usual shear. This is an easy exercise. But you also need a map from X of R here, right? So that was our goal. So we don't only we need them. So because our goal was not only to construct X prism question mark, we also want to have a map from X times ZP prism to this object. So we want to have a map from this set to this group point. That's slightly trickier here. So it's not that bad, but maybe again, this is where some derived algebraic geometry is used. Very little, but you still don't need to know what the potential complex is. It's some deformation. Well, I mean, I don't know. I can continue and explain proof now, or
no. This would be. Of course, you can explain, but we will not understand everything. So I'm afraid that you have to figure out now, or
yeah.
you wish.
So that's what remains to do.
So what will happen next time, and when will it?